Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 11, Lesson 6 on the basic graphs of the sine and cosine functions. So now we really get into it, right? We want to learn what the sine and cosine functions graphs look like and how we can eventually use them to model various physical phenomena. And to put it mildly, they are some of the most important functions out there when it comes to modeling different things, especially phenomena that are called wave phenomenon, light, sound, tides, all sorts of things like that come and go can be modeled using the sine and the cosine functions. And let's start to understand how that is done in this particular lesson. All right, here we go. The graphs of sine and cosine. The sine and cosine functions are some of the most important in all of physics and engineering. The sine and cosine functions are used extensively to model what are known as periodic phenomena, those that repeat. In this lesson, we will learn how to graph them by considering their outputs at the top, bottom, left, and right most portions of the circle. And as a reminder, those are the portions of the circle that are called the quadrantal angles. Those are 0, 90, 180, 270, 360, etc., or multiples of pi over 2 in terms of radians. And you'll be excited to know all of this modeling gets done in terms of radians. That was a little bit of sarcasm there for you to begin this lesson. All right, let's take a look at exercise number 1. Consider the functions f of x equals sine x and g of x equals cosine x, where x is an angle in radians. By using the unit circle, fill out the table below for selected quadrantal angles, multiples of 90 degrees. All right, now again, we use the radian as the input in these sorts of functions because they have a physical meaning, right? On the unit circle, the radian literally is the length of the arc that you travel around, all right? It's not just the angle, but it's also how far you've traveled around the unit circle. Now, remember this basic fact. Never forget, right? The cosine of an angle is equal to the x-coordinate on the unit circle, and the sine of the angle is equal to the y-coordinate on the unit circle. So let's just talk about the easy ones, 0, pi over 2 pi, 3 pi over 2, and 2 pi, and let's start with the cosine function, right? If I go to an angle of 0 radians on the unit circle, the x-coordinate is equal to 1. So the cosine of 0 is equal to 1, right? Then I move to the top of the circle, right? And we're going to travel in a positive direction initially. All right, we're going to travel counterclockwise initially. So I go to the top of the circle, pi over 2 radians, and now my x-coordinate is equal to 0. Right? I then travel all the way to 180 degrees or pi radians, and now my x-coordinate is -1. And then I travel down to the bottom of the circle, 3 pi over 2. Let me get that a little bit more on here. 3 pi over 2, and now my x-coordinate is back to 0. And then I travel all the way to 2 pi, and my x-coordinate is back to 1. Now, I want to be very clear, right? This table doesn't stop there. I could then go up to 2 pi plus pi over 2, which would be 5 pi over 2. Then I'd have 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, 10 pi over 2, etc. These are periodic phenomena, meaning that I'm going to keep going 1 to 0 to -1 to 0 to 1 to 0 to -1 to 0, etc. Now, if I want to go to the negative angles, right, if I want to go sort of in this direction, we're now going to be traveling clockwise, right? So I'm going to be going this way. This is negative pi over 2. This is negative pi. This is -3 pi over 2 and -2 pi. Right, coterminal angles. So if I go to negative pi over 2, my x-coordinate is 0. If I then go to negative pi, my x-coordinate is -1. If I go up here to -3 pi over 2, my x-coordinate is back to 0. And if I go all the way to -2 pi, my x-coordinate is back to 1. So I have now used the unit circle and the definition of cosine as the x-coordinate on the unit circle to generate a rough table of values for the cosine. And notice, right, all cosine values are between -1 and positive 1. Now you might be wondering to yourself right now, but what about pi over 3 and pi over 4 and pi over 6 and 5 pi over 6 and 4 pi over 3 and all of that? Well, these are good enough. They're going to be good enough to help us create the graphs and understand the graphs of cosine and sine. We don't need all those other special values to help us out. We could have them in a table, but all they would do is give us these ugly radicals all over the place. I'd like you to pause the video now and see if you can fill out the line for sine, given that the sine of any angle is the y-coordinate of each one of these coordinate points. Pause the video now and go ahead and do that. All right, well, at 0 radians, our y-coordinate is 0. At pi over 2, our y-coordinate is 1. At pi, our y-coordinate is 0. At 3 pi over 2, our y-coordinate is negative 1. At 2 pi, our y-coordinate is back to 0. Traveling clockwise, at negative pi over 2, our y-coordinate is negative 1. At negative pi, our y-coordinate is 0. At negative 3 pi over 2, our y-coordinate is 1. And at negative 2 pi, our y-coordinate is back to 0. All right, and sine, you can really see the periodicity, right? That's a cool word, periodicity, right? We are at 0, go up to 1, back down to 0, go down to negative 1, go back up to 0, go up to 1, go down to 0, go down to negative 1, etc. It's a little bit harder when we're thinking about left-right, which is what cosine is, versus sine, which is kind of up-down. Now, where do we go with that? Well, letter B. Graph both the sine and the cosine curves on the grid shown below. Clearly label which curve is which, then verify on your calculator, make sure it's in radian mode. Fantastic. All right, so right now I have the x-axis, which is the angle, okay? The input is the angle, the output is the sine and the cosine value, okay? Don't get that confused with the x-coordinate and the y-coordinate on the unit circle, totally different, right? Input is the angle. I've already got it marked off in pi over 2 increments, okay? So let's go ahead and do cosine first. So at an angle of 0, right, I have a cosine value of 1. At an angle of pi over 2, I have a cosine value of 0. At an angle of pi, I have a cosine value of negative 1. At an angle of 3 pi over 2, I have a cosine value of 0. And at 2 pi, I have a cosine value of 1. At negative pi over 2, I have a cosine value of 0. Then a cosine value, made that go a little bit too low. I apologize for that. I have a cosine value of negative 1. Then 3 pi over 2, a cosine value of 0. And negative 2 pi, a cosine value of 1 again. Now, how do I connect these dots? Well, what I'm not going to do, even though it seems like I should be able to, is connect them with straight line segments. I don't get what's called a sawtooth function. I get almost something that looks like some parabolas that are sort of inverted like that. All right, so that is y equals the cosine of x. Okay, I'd like you to pause the video right now and graph y equals the sine of x, and you're going to get a curve that basically looks identical to this, but just shifted by pi over 2 units. Pause the video now and go ahead and do that. Okay, well, let me switch over to red just so that we can really see the distinction between them. At 0, we have a sine value of 0. At pi over 2, a sine value of 1. At pi, a sine value of 0. 3 pi over 2 has a sine value of negative 1, and 2 pi has a sine value of 0. At negative pi over 2, we have a sine value of negative 1. Negative pi has a sine value of 0. Negative 3 pi over 2, a sine value of 1. And negative 2 pi, a sine value of 0. Yet again, connecting these with a nice smooth curve, we'll get y equals sine x. And if you're saying again to yourself that those are exactly the same curves, right? If you took cosine and you shifted it pi over 2 units to the right, you'd lay on top of sine, or vice versa, shift sine pi over 2 units to the left and you'd land on cosine. That's a great observation. They are essentially the same curve. Actually, they are identically the same curve, just horizontally shifted from one another, okay? And I also want to emphasize something else. they continue in both directions. In fact, let's put little arrows on here, okay? They don't just end here, all right? They continue forever. We just have to stop the table at some point, right? We can't like have the table go forever. We have to actually like stop it at some point, all right? But we can keep going around the unit circle, right? We can have angles of 600 degrees and negative 2,000 degrees. And there will still be x and y coordinates on the unit circle. These things just keep going. That didn't work. These just keep going forever in this direction and keep going forever in that direction. Now, let's keep going. And actually, let's bring a nicer picture up there, right there. So, letter C. Classify the sine and cosine functions as even, odd, or neither. Right? Remember, even functions are functions that say, well, for opposite outputs, we get the same input. And odd functions say for opposite inputs, we get opposite outputs. Also remember, even functions have symmetry across the y-axis, and odd functions have symmetry across the origin. So pause the video now and tell me whether cosine of x is even, odd, or neither, and whether sine of x is even, odd, or neither. All right, well, cosine happens to be an even function, and sine is an odd function. Okay? And you can really see that in the table of values, right? If I look at cosine, say I take negative pi and pi. Look at those two outputs. They're the same, right? If I take negative 2 pi and positive 2 pi, and I look at those outputs, they're the same. Cosine doesn't care whether the angle is negative or positive, all right? And that's kind of nice because if you know that the cosine of, let's say, pi over 3 is positive 1/2, then the cosine of negative pi over 3 must also be positive 1/2. On the other hand, sine is an odd function, and you can see that as well. If I get rid of all of this, and I go to negative pi over 2 and positive pi over 2, and I look at the two sine values, they have opposite values. And again, what's great about that is if you know that sine is an odd function, and let's say you know the sine of pi over 3 is root 3 over 2, then you would know that the sine of negative pi over 3 would be negative root 3 over 2. So there's some really nice advantages of that. You can also see that even odd nature in the symmetry, right? Clearly, if we look at the blue graph here, if we reflected it across the y-axis, it would land on itself. And also, maybe not as clear, but if we took the red graph and we rotated it 180 degrees about the origin, it would also land on itself, right? This point would rotate down to this point would rotate over to that point, etc. All right, very important. Let's take a look at letter D. The domain and range of sine and cosine functions are the same. State them below in interval notation. All right, so I'm claiming it doesn't matter whether you're talking about the sine or the cosine, the domains and the ranges are the same. Now, the domains, remember, are the allowable angles that will give you an output, and the range is what those outputs are. Pause the video now and see if you can think about what the domain and the range of these two functions are. All right, well, this is cool. Now, it would be very tempting to say that the domain is negative 2 pi to 2 pi, but that would have meant that you had ignored me when I said you can just keep going around the circle forever. The domain of both sine and cosine is every angle from negative infinity to positive infinity. There is no angle that we can't travel around the unit circle, eventually stop, get a coordinate pair, and plot it, all right? This is just a small image of the sine and cosine functions. Now the range, on the other hand, the actual outputs, those go between negative 1 and positive 1, right? There is no way to get either a sine or a cosine value that is outside of the interval negative 1 to 1, all right? And on top of that, every single value between here gets hit. These are continuous functions, and we will hit every y value between -1 and 1, every output value. Now, letter E. This one's important, as if the others weren't. After how much horizontal distance will both the sine and the cosine functions repeat their basic pattern? This is called the period of the trigonometric graph. Because these graphs have patterns that repeat, they are called periodic. All right, so this is really critical, and it also will make all the sense in the world. What we're saying here is, let's say that we just take, I'm going to go with black. Let's say that we take this and we start to draw out this cosine curve. Right here, right, it would start to repeat. This is what's called the period. It is how long it takes before the fundamental waveform repeats itself. And that is both, for both of them, 2 pi radians. And that makes sense because that's how far we have to travel around the unit circle. And it doesn't matter where we start on the unit circle. You know, if I started on the unit circle here, let's say, I would still have to travel 2 pi radians to get back and begin my pattern all over again. Now, that's not to say that, like, if you're like, let's say right here at pi over 2, you don't hit 0 again here. But I have to go through an entire 2 pi radians before the entire thing repeats itself. Another way to look at it is, if I took either one of these curves, how far would I have to horizontally shift it before it laid on top of itself again? All right, but every 2 pi radians, either one of these graphs is going to repeat its basic shape. All right, very important, known as the period of a trigonometric graph. Now, we're going to do just a little basic transformation work in this lesson of trigonometric functions, and then we're going to see it a lot more in the next few lessons. So let's do a reviewing a basic transformation. We would now like to look at a very basic transformation of the two functions, but first, a review. Exercise number 2. I can't believe we're just on exercise number 2 now. Let's take a look. Given a function f of x and a function g of x equals a times f of x, where a is a constant, explain how the graph of g of x will compare to f of x if, in a is greater than 1, if b, a is between 0 and 1, and c, a is less than 0. All right, so again, we did a whole unit on function transformations, and this is just merely one type, or maybe 2 types, depending on how you count. And what I'm asking is, if I take a function, any function, not just a trig function, but any function, and I multiply it by a constant, what happens if that constant is greater than 1? What effect does it have on the graph? Pause the video now and think about this for a second. Well, if a is greater than 1, that's going to be a vertical stretch by a factor of a. Now, let me give you a little preview, right? Think about this for a moment. The highest that the sine and cosine value goes is 1, and the lowest it goes is -1. So if I stretch it by a factor of a, the highest it's going to go is positive a, and the lowest it's going to go is negative a, right? And that makes sense, right? If the biggest y value originally is 1 and the smallest y value is -1, and then I multiply by a, well, then the highest it's going to go is positive a, and the lowest it's going to go is negative a. Now, if a is between 0 and 1, we don't get everything I just said still applies. We just don't get a vertical stretch. We get a vertical compression by a factor of a. Now again though, with sine and cosine, whatever, right? Normally they go between -1 and 1, -1 and 1, back and forth, right? Back and forth, these graphs go between -1 and 1 and -1 and 1. If I suddenly multiply the whole graph by 1/2, now they're going back and forth between 1/2 and -1/2. That's the beautiful thing about these things going back and forth between 1 and -1. And you could almost say to yourself, what that means is that I'm putting myself now on a circle that doesn't have a radius of 1, but that has a radius of a, right? And now I'm going around that circle, and I'm looking at these x and y coordinates that are going back and forth between a and -a. Now, what if a, though, is less than 0? All right? So what if a was -1? What if a was -5 or -1/2? That's going to combine two things, right? This is going to be a combination of a reflection across the x-axis along with a or b, right? So if I multiply by -3, I'm going to flip the graph across the x-axis and I'm going to stretch it out by a factor of 3. If I multiply by -1/4, I'm going to flip it across the x-axis and then compress it by a factor of 1/4. So tossing in a negative there has the effect not only of stretching and compressing, but also reflecting across the x-axis. So let's play around with this, though, with the two functions sine and cosine. Vertically stretching, compressing, and reflecting. Exercise number 3. Consider the function f of x equals cosine of x shown graphed below. If g of x equals 3 times f of x, find a formula for g of x and sketch it on the grid using what you reviewed in exercise number 2. Awesome. Well, the formula is really a piece of cake, right? G of x is going to be 3 times the cosine of x. Ooh, hard, right? But then think about this, right? Now I've got my cosine graph, and all I'm doing is taking every y value on here and multiplying it by 3. Now normally that would be kind of a pain, right? Because for a normal function I might be like, well, here I've got -2, so I'll have to multiply it by 3. Here I've got 5, and I'll have to multiply it by 3. But cosine and sine just bob up and down between -1 and 1. So what do? Well, I go over here to 3, maybe I'll go in red, or I go over here where we've got y equals 1, and I go up to y equals 3. Now remember, right, when I have a y value of 0 and I multiply by 3, those don't go anywhere. And now that y value of -1 will go down to -3 and 3 and -3 and 3 and whoops, sorry. Got way ahead of myself there. Don't know what I was doing there. Right? So everywhere I had a y value of 1, I now have a y value of 3. Everywhere I had a y value of -1, I now have a y value of -3. And now my graph's going to do something like that. All right. Isn't that cool? Let's take a look at another one of these. Letter B. If h of x equals -4 times f of x, find a formula for h of x and sketch it on the grid using what you reviewed in exercise number 2. All right, well, I'd like you to pause the video and think about this. Now keep in mind, everywhere you now have a y value of 1, when you multiply that by -4, you'll then have a y value of -4. Everywhere you have a y value of -1, when you multiply it by -4, you'll then have a y value of +4. I'm going to end up drawing this graph in black just to give us a third color. Pause the video now and see if you can then draw the graph of h of x. All right, let's do it. So here we go. Let me go into black. All right, so here we have a y value of 1. Now I'll have a y value of -4. That y value of 0 is going to stay fixed. Here the y value of -1 is going to become a y value of 4. That y value of 0 will be fixed. Here a y value of 1 will become a y value of -4. Y value of 0 stays fixed. right? 0 times negative 4 is still 0. Here a y value of negative 1 will become a y value of positive 4, fixed, and negative 4. So now we will have that. All right, let me just label that's h of x equals negative 4 cosine x. Whoops, nope, 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 that's good. Let's put it in red. We'll have g of x equals 3 times f of x. And of course, our original curve is just f of x equals cosine x. I just want to have these things labeled, right? And color-coded. Awesome. All right, let's do a little graphing on the calculator. Letter C. Verify both graphs using your calculator. All right, we haven't ever done any trigonometric graphing on the calculator, so let's take a look on the TI Inspire, how we can do some trigonometric graphing. Whew, mouthful. All right, so as usual, I'm just going to add a graph. And let's do the first thing. Let's make sure that our calculator's in radian mode, and it in fact is, right? It says RAD up here. If it doesn't say RAD, if it says DEG, just hover the pointer over that and click on it, and it'll switch it to radians. There we go, and then it messed with my graph grid as well. That was weird. So now I'm going to go into Menu. I'm going to go into Graph Edit. I'm going to enter my function, and let's put cosine x in first, right? Now we're going to have fun. Oh, it didn't go all crazy on me. That was nice of it. All right, so I'm going to have cosine x. I'll put the other ones in a moment. I'm going to hit enter. Now, right now I have a grid on, and you very well may not have a grid on. Let's get this thing kind of set up the way we want it. I'm going to go into Menu. I'm going to go into my window settings. All right, I want negative 2 pi as my x min. I want 2 pi as my x max, and I want it to go, oh my goodness, come on. There's my irritable calculator. I want it to go by pi divided by 2 along the x-axis. Along my y-axis, I'd like it to go from negative 5 to 5, and I'd like it to go by 1s. Okay, so again, let me just be very clear. Right, my graph settings, I want it to look exactly like this graph. This graph goes from negative 2 pi to 2 pi. Along the x-axis, it goes by pi over 2 increments. My y-axis goes from negative 5 to 5 by 1s. I hit OK, and I've got my graph. Now, I've got this nice graph grid on there. If you don't have that on yours, what you do is you go to Menu. Down here, number 9 is Settings. And here it says lined grid. Now, if I don't have lined grid on, if I have just no grid, this is the way it looks, which is nice. There's nothing wrong with that, but it's a little bit hard to kind of see what's going on compared to this. That's why I really like, in my settings, having a lined grid on. I prefer that to the dotted grid. The dotted grid's a little bit weird. But now, this literally, I mean, I can almost lie it on top here. Now, the one thing is your calculator along the x-axis is not going to show you pi over 2, 2 pi, etc. Notice it shows 1.571. That's pi divided by 2, accurate to 3 decimal places. It also shows a 6.283. That's 2 pi, accurate to 3 decimal places. So there is my cosine of x. Now, we also had 3 times cosine of x and negative 4 times cosine of x. So let's put those in as well. Here we go, graph entry edit, function. So we had 3 times cosine of x. There we go, nice. And then we had, whoops, nope. We had negative 4 times cosine of x. And there we have it. And those were exactly what we had before. Right? And again, notice the basic waveform, cosine x. By the way, one thing that you're going to want to know right away is that cosine starts at its maximum. And by starts, I mean the y-intercept is at its maximum, 1. The sine graph actually starts at its what's called midline. It starts at the origin. But notice all I did, right, when I multiplied it by 3, I just took that and stretched that up by 3, a factor of 3, stretched that down by a factor of 3. On the other hand, when I multiplied by -4, I took that and flipped it across the x-axis and stretched it down by a factor of 4. All right, cool, right? We get this beautiful wave form that would continue forever in that direction and forever in that direction. All right, let's put that away for a little bit. If you think I like trigonometric graphing, you're absolutely correct. I think it's one of the coolest things that we do in this course. And one of the things I love about it is it has so many applications. Anything that comes in waves, this applies to. Now for you, that is mostly going to be sound waves and light waves, all right? But we can make a lot of, sort of draw a lot of real physical understanding about what we're doing right now, especially in terms of sound. And those of you that play musical instruments, I'll try to make connections to that as well. Starting with what's known as the amplitude of a wave. As we can see, the coefficient, right, multiplying the cosine function controls the height that the cosine curve rises and falls above the x-axis. Its absolute value, right, the absolute value, so in that case where it was -4, I just want to think about 4, right? Its absolute value is called the amplitude. In terms of sound waves, it indicates the volume of the sound. So literally, right, when I went from just cosine x to 3 times cosine x, I literally turned the volume up by a factor of 3. Now, when I went to -4 cosine x, I actually turned the volume up by a factor of 4. All right, and I won't try to go loud there again. But the amplitude is true whether you're talking about the sine function or the cosine function. It is literally the distance that we rise above and fall below what's called the midline of a sine or cosine curve. And it is defined as simply the absolute value of that coefficient. So even if the coefficient is negative, I just want the absolute value. We're going to be talking about the amplitude a lot as we go through the last few lessons of this unit. Just keep in mind, we just saw the amplitude. Now let's play around with a little bit of amplitude work with the sine curve. Exercise number 4. The basic sine curve is graphed below, without the use of your calculator. Sketch each of the following sine curves on the axes below, then check using your calculator. All right, so this is exactly what we were just doing, right? We now have our sine curve, and again, notice that the sine curve, unlike the cosine curve, starts at the origin and then rises out of it to hit its maximum, then goes back down to the x-axis, then goes down to its minimum, then comes back up. The cosine always kind of starts at its maximum. The sine curve starts at this sort of midline and then goes up and down. But it now works out exactly like it did before. So let me switch over to red, right? Again, the beautiful thing is sine and cosine naturally go between -1 and 1. So 2 times the sine of x will just naturally go between -2 and 2, right? So I come over here at pi over 2, and now I go up to 2 and down to -2, and those x-intercepts just get fixed, right? You almost can't get any easier than that. And all of a sudden, you get y equals 2 times the sine of x. I'm going to run out of colors really quickly. Okay? And let's do that one with y equals -3 sine x together. Right? This one is going to be very, very similar. The big difference is we're not only going to get that stretch by a factor of 3, but we're also going to get a reflection across the x-axis. So maybe if I do that one in black, and then I run out of colors. Right here, at that 1, I now would be down at -3. 0 stays at 0. -1 goes up to +3. So we end up getting a graph that kind of looks like this. And that is y equals -3 times the sine of x. Nice, right? Amplitude of 2, amplitude of 3, not an amplitude of -3. The only thing that negative is doing is sort of flipping across the x-axis. Another nice situation where you can think about sine and cosine curves is sort of the daily cycle of how many hours of daylight you get in a given day, right? So during the summer, right, you're hitting kind of a maximum. During the winter, you're hitting a minimum. Keeps going year after year after year. And you can think of like a negative as being sort of in, let's say, the southern hemisphere, as opposed to the northern hemisphere, right? All of a sudden that yearly cycle flip-flops, right? We still get the same sort of amplitude. It goes up, it comes down, it goes up, it comes down in terms of the amount of daylight we're getting. But, right, it's kind of like in a reverse direction in terms of when you're getting it, spring and fall. Okay, what I'd like you to do is go ahead and pause the video now and graph y equals 4 times the sine of x, and a little more challenging, y equals -1/2 times the sine of x. Do the best jobs you can on here. It doesn't have to be perfect. All right, well, I got to be kind of a little redundant with color now. I apologize for that. I can't really use green because I'm on a green screen right now. I'm not even up here. This is just an avatar of me. So anyway, when we have, I'm kidding. When we have y equals 4 times the sine of x, right? Again, my x-intercepts are going to be fixed, but that 1's going to stretch up to a 4, and that -1 is going to stretch down to a -4, right? And here then we have that -1 down here to -4, up here 4 and 0. So we're going to get something like that. Maybe one day it'll be an avatar, but not yet. Oh man, I totally missed that. I do kind of want it to go through that point. I shouldn't have it completely miss the points. I got a little bit too flipped there. I apologize for that. Y equals 4 sine x. I have to stop making jokes and talking at the same time. Let me now maybe go, yeah, I guess I'll go red on this one. Tough. There's only so many colors. So now I'm going to do this one in red. And again, here we're going to get a compression, which is a little bit tricky, and a flip. So again, we've got this 1 going down to a -1/2, right? Then we fix that, then a +1/2, then back to 0, up to +1/2, down to 0, down to -1/2, up to 0. So we're getting quieter on that curve. We're flipping it and we're getting quieter. So we get y equals -1/2 sine x. And I'll leave it up to you to verify that unbelievably beautiful picture on your calculator, all right? And again, that's easy enough. I encourage you to go ahead and do it. More than anything else, to kind of get used to setting a graph grid up to be able to use your calculator on it. All right. So let's wrap this up. Today, we looked at the most basic signs, the most basic graphs of the sine and the cosine function. And believe it or not, we left most of the ugliness of the unit circle in the past. Don't get me wrong. You still need to know things about the sine and the cosine of pi over 3, pi over 6, pi over 4, reference angles, all of that. Okay, that's not gone forever. We're going to have to revisit it towards the end of this unit. But for right now, it's good enough to just be able to think about the sine and the cosine values at what are known as the quadrantal angles. Those are 0, 90, 180, 270, 360, or in radians, 0, pi over 2, pi, 3 pi over 2, 2 pi, and likewise in the negative direction when we go clockwise around the circle. What's wonderful is because going around the circle continually repeats the x and the y coordinates that we end up seeing on the unit circle, we get these beautiful waveform patterns, all right? Periodic phenomena that repeat every 2 pi radians as we go around the circle. Now, once we take those two patterns and we multiply them by some kind of constant, we stretch the graphs out or we compress them down, and if we multiply by a negative, we also reflect them across the x-axis. That multiplying constant, or at least its absolute value, is known as the amplitude of the wave, all right? And in terms of sound, it literally means the volume. That's why an amplifier, right, is something that increases the volume of, let's say, your stereo or of your iPhone or whatever, right? An amplifier, in more general terms, increases sort of the magnitude of any type of wave that you look at. We're going to be talking about a lot of different transformations in terms of trigonometric functions, specifically the sine and the cosine function, and we'll try to keep relating them back to things like sound and light and other wave phenomenon that you should be at least a little bit familiar with at this point in your life. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.